Okay, so welcome back to this advanced manufacturing and process modeling course. So today we are going to start with the process modeling aspects in case of fusion welding processes. So let's go into that. So these are basically the content, that is analytical method and boundary element method to solve the heat conduction equation applied to welding processes, finite volume based multi-phase flow model of melt pool transport phenomena and solidification during fusion welding, and also thermomechanical modeling of the residual stress evolution during welding processes. Okay. So, as we know that many heat conduction problems encountered in engineering applications involve time as an independent variable. So, the goal of the analysis is to determine the variation of the temperature with respect to space and time. Okay. So, within the heat conducting body. So, in general we deal with conducting bodies in a 3D dimensional Euclidean space in a suitable set of coordinates, for example x y z and or r theta z. So, and the goal is to predict the evolution of the temperature field for future time steps, that is t greater than 0. So, here we investigate specifically solutions to selected special cases of the following form of the heat equation. So, what is the form of the heat equation? So, that is rho Cp del T del T, capital T stands for temperature, small t stands for the time, is equal to grad K grad T plus Gr. Okay. So, let us see. So, the analytical method is applicable to simple geometries and boundary conditions only. So, the components of the heat flow per unit area, that is heat flux Q double prime in the x and y directions, are obtained from Fourier's law, which states that Q x double prime is equal to minus k dt dx. K is nothing but the thermal conductivity, and Q y double prime is equal to minus k dt dy. It should be dy. So, this is a mistake. Please correct. So, the heat heat flux depends on the temperature gradient and is therefore a vector, while temperature is a scalar. So, so the heat flux Q double prime at a given point x y is the resultant of the components Q x double prime and Q y double prime as discussed above. So, at that point and is directed perpendicular to the isotherm. So, if the temperature distribution in a system is known, the rate of heat flow can easily be calculated. So, therefore, heat flow analysis usually concentrate on determining the temperature field, and based on the temperature field the heat flow can be assessed. So, let us consider a simple case of a thin rectangular plate as shown over here. So, this is the rectangular domain where we are focusing on to evaluate the temperature distribution. So, where the boundary condition, so it is free from heat sources and insulated at the top and bottom surfaces. So, accordingly T is equal to 0 at the top and bottom surfaces. Okay. And so, the for steady state 2 dimensional heat conduction in the absence of any heat source and uniform thermal conductivity, Laplace equation holds good, which what is that? That is del square T del x square plus del square T del y square is equal to 0. So, that means grad square T is equal to 0. So, this is the Laplace equation. And then, so now moving ahead, since del T del Z equivalent to 0, that is in the z direction, temperature hardly changes. So, it is equivalent to 0. So, the temperature is a function of x and y alone, and if k is uniform, that is thermal conductivity. So, the temperature distribution must satisfy a linear and homogeneous partial differential equation that can be integrated by assuming a product solution for T x y of the form. So, capital T is equal to x function of small x, capital Y function of small y. So, so where x is equal to x function of x is a function of x alone, and y is equal to y function of small y, a function of small y alone. So, differentiating twice, first with respect to x and then with respect to y, we can get so del square T del x square. So, you can see that so what we can get. So, first derivative del T del x, then we will get y del x del small x, and then del square T del x square is equal to capital Y del square x del x square. So, this is what is I mean written sorry yeah. So, this is what is shown over here, and similarly in case of y direction. So, del square t del y square is equal to capital X del square capital Y del small y square. So, this is how we can differentiate twice the above function, that is written at the top. Okay. So, if I term at equation 1, so from equation 1 if we differentiate twice with respect to x and then with respect to y, then we come to these two set of equations, we are terming as equation 2, and then so then substituting in above equation. We can get that the y. So, here we know the so this is the expression, that is the Laplace equation del square t del x square plus del square t del y square is equal to 0, and now we have individually evaluated the values of del square t del x square and del square to del y square. So, if we just club them, so then so basically we are putting the values of del square t del x square and del square t del y square over here, and then we are arriving at this expression, that is capital Y del square capital X del x square plus capital X del square capital Y del by del small y square is equal to 0. Or we can rearrange the term. So, you can see that del square x del x square. So, from this equation we can get if we just take it to the, so del square capital X del x square y is equal to minus capital X del square capital Y del y square. So, and then if we multiply by minus on both the sides, and then we bring the x in the left hand side, then 1 by x del square capital X by del x square is equal to 1 by y del square y by del y square is equal to delta square. Okay. So, then the variables are now separated. So, the left hand side is a function of x alone, while the right hand side is a function of y alone. So, since neither side can change as x and y vary, so both must be equal to a constant, say delta square. So, we have therefore two ordinary differential equations. So, what are they? So, you can see, so if I take this to this side, because both the equations are equated to with delta square. So, then we can write that d square capital X by d small x square and plus delta plus del square or delta square capital X is equal to 0. Similarly, for in case of y, we can write that d to capital Y d small y square minus delta square capital Y is equal to 0. So, from these two these equations, this set of equations are coming. So, because this x is function of x alone, y function of y alone. So, in spite of partial derivative, we can write them in the form of ordinary differential equations. So, that is what is done over here, and then moving ahead. So, now yeah, so the general solution of the equations shown over here. So, if I term them as equation set 3, so then the general solution for equation x capital X is equal to C1 cos delta x plus C2 sin delta x, and the general solution for capital Y is equal to C3 e to the power minus delta y plus C4 e to the power delta y. So, therefore, from equation above we can write, because we know that t is equal to capital X into capital Y. So, then from this we have identified the general solution for capital X and capital Y. So, we can readily write from here, using the values for x and y, we can arrive at this expression, that is capital T is equal to C1 cos delta x plus C2 sin delta x multiplied by C3 e to the power minus delta y plus C4 e to the power plus delta y, okay, where C1, C2, C3 and C4 are constants calculated from the boundary condition. So, as shown, so then now if we go back to this 2D domain where we are trying to identify the temperature distribution. So, we know that so that you see that at x is equal to 0, t is equal to 0, right. Yeah, so at x is equal to 0, t is equal to 0. Again, if I go back to this expression, so you can see that at x is equal to L, again T temperature is equal to 0. So, that is our second condition, that is x is equal to L, T is equal to 0. And then T is equal to again if we go back, so then you see that at the at the y is equal to 0. So, at the base again t is equal to 0. So, that is our third condition, that is at small y is equal to 0, t is equal to 0, okay. And then at the we can see that so at the when y is equal to b, then we can see that t is equal to T m sin delta x by L. So, that is our fourth condition, okay. So, t is equal to T m sin delta x by L at y is equal to b. So, substituting these equations, so from the third condition, if we take up the third condition first, that is at t is equal to 0, at y is equal to 0. So, then we can get here that so C1 cos delta x plus C2 sin delta x. So, it is coming from here, because we have written already that capital T is equal to C1 cos delta x plus C2 sin delta x multiplied by C3 e to the power minus delta y plus C4 e to the power delta y. So, now if we write that y is equal to 0, so then e to the power 0 it becomes 1. So, then C3 plus C4, C3 plus C4, C1 cos delta x plus C2 sin delta x is equal to 0. And then if we go to the condition, first condition, that x is equal to 0, t is equal to 0, again we put this value in this expression, that t is equal to capital X into y. So, then we know that x 0, if x is equal to 0, then cos 0 becomes 1. So, then C1 plus C1 and sin 0 is equal to 0. So, then C1, and here there is no x is there. So, then it will be that C1 multiplied by C3 e to the power minus delta y plus C4 e to the power delta y, yeah. So, is equal to 0, okay. So, because x is equal to 0, t is equal to 0. So, this is the expression for t. And then from the second condition, what was the second condition? That is t is equal to 0 at x is equal to L. Again, if we put that in this expression, so then what it will become? Then C1 cos delta L plus C2 sin delta L, C3 e to the power minus delta y plus C4 e to the power delta y is equal to 0. Okay. So, this is what is written over here. Okay. So, then we have already utilized the three conditions. Now, we will move ahead to use the fourth condition. So, before that, so you can see that so from the second equation, so second condition. So, what is the second condition we got? So, so that is the so that is the second condition. So, that is C1 cos delta L plus C2 sin delta L multiplied by C3 e to the power minus delta y plus C4 e to the power delta y. So, from here we can write that C3 is equal to minus C4, and so the if C1 also equal to 0. So, then we can write here that 2 C2 C3 sin delta L sin delta y is equal to 0. So, to satisfy this condition, sin delta L is equal to 0 or delta is equal to n pi by L. So, then so sin n pi is equal to 0. So, that is why so where n is equal to 1, 2, 3 can be, any value can be possible. So, therefore, a different solution for each integer n, and each solution has a separate integration constant C n. So, summing these solutions, we can write from the following expression, that is T temperature is equal to summation of n is equal to 1 to infinity C n sin n pi x by L sin hyperbolic n pi y by L. Okay. So, so the last boundary condition needs, that is that at y is equal to b. So, then that is what I mean. So, now we have evaluated the value of temperature, okay, using the other boundary conditions, that is at x is equal to 0, at x is equal to L, and at y is equal to 0. So, then this is if we consider the value of n is equal to 1. So, from this expression we can arrive at this expression. So, then what it will become? Then it will become C 1 n sin pi x by L sin hyperbolic pi y by L. So, then because I mean we know that y is equal to b, t is equal to T m sin pi x by L, that is what we have seen over here. Yeah. So, T m sin pi x by L. Now, if we put the value of t is equal to T m sin pi x by L, and if we put the value as y is equal to b. So, then from here, as we have considered n is equal to 1. So, then finally, the expression becomes, so t is equal to T m sin pi x by L is equal to C 1 sin value of n is 1 sin pi x by L sin hyperbolic pi y by L, pi b. So, because y is equal to b, so pi b by L. So, then from here we can evaluate the value of the constant C 1. So, then I mean C 1 becomes equal to T m by sin hyperbolic pi b by L. So, the solution therefore becomes T x y is equal to I mean T m sin hyperbolic pi y by L divided by sin hyperbolic pi b by L into sin pi x by L. So, this is the analytical solution of the heat equation, that is Laplacian equation. So, but that is only possible for simpler domains. The moment there is complicated domains, we are I mean utilizing I mean going for the solution of the I mean temporal I mean thermal evolution in case of a weld joint. So, then it is not possible to solve the I mean temperature profile using analytical I mean technique. So, then we have to take resort to the numerical techniques that we have discussed already in several times before, like the available techniques, finite element, finite volume and finite difference. So, here we will show an example of finite volume formulation. So, how we can basically estimate the temperature evolution within a melt pool, I mean within a weld melt pool. So, before that we will I mean discuss about the heat conduction equation by boundary element method. So, boundary element method, the key I mean the key technique in boundary element method is multiple reciprocity method. So, so the multiple reciprocity method is a general method of transforming domain integrals arising in boundary element method for thermal problems. So, these integrals have the following form, that is d 0 is equal to integration domain integration. So, omega integration omega b 0 u 0 asterisk d omega, where omega is the stands for a region under consideration, u 0 asterisk is a fundamental solution, and b 0 represents arbitrary function of coordinates, that is heat source generation rate and temporal derivative of temperature, etc. So, I mean so that the fundamental solution and analog of a heat flux can be I mean defined as K, that is thermal conductivity, I mean grad square u 0 asterisk is equal to I mean delta I, that is a Dirac's function acting at point I and K. Acting at point I, and K is the thermal conductivity as I told before, and I mean and Q 0 asterisk is equal to minus Q minus K del u 0 asterisk by del n. Okay. So, I mean so that is the heat flux. And so, now where as I told that delta I is Dirac's function acting at point I and K is the thermal conductivity. So, del n stands for the outward normal derivative. So, in order to transform integral into boundary, one can introduce function u1 asterisk and its normal derivative associated with fundamental solution u0 asterisk by formula I mean grad square u1 asterisk is equal to u0 asterisk, and as we have mentioned earlier, the heat flux q0 asterisk. Similarly, in case of I mean q1 asterisk, we can express it as is equal to minus k del u1 asterisk I mean divided by del n. So, so it is the similar form. So, then thus applying the reciprocity theorem, the domain integral d0 can be evaluated as follows. So, d0 is equal to domain integral b0 u0 asterisk, as we have already mentioned that b0 represents arbitrary function of coordinates. Okay. So, then b0 u0 asterisk d omega is equal to. So, now we have also defined that that u0 asterisk is equal to we have defined here. So, u0 asterisk is equal to del square so u0 asterisk is equal to just a minute, u0 asterisk is equal to del square u1 asterisk. So, then here if we put the value of u0 asterisk, so then it becomes the domain integral d0 takes the following form, that is integration omega b0 in spite of u0 asterisk we put the value del square u1 asterisk into d omega. Now we can solve this by integration by parts. Okay. So, that is u v dx. So, here u is equal to is b0 and v is nothing but grad square u1 asterisk. Okay. So, then if you solve that, and then as we know that if we consider the value of w0 is equal to minus k del b0 del n. So, then we can write from this, we can solve this expression and arrive at this form, that is 1 by k integration domain integration del u1 asterisk u1 asterisk w0 sorry. So, w0 that is we have transformed b0, that is the the arbitrary function into a weight function w0. So, then u1 asterisk w0 minus q1 asterisk b0 d delta d del plus capital D1. Okay. So, then you can see the, so then it is domain integral, the d1 has the form is equal to integration omega u1 asterisk del square b0 into d omega. Okay. So, calling b1 is equal to grad square b0 and w1 is equal to minus k del b1 del n. So, one can arrive at that d1 is equal to integration omega u1 asterisk b1 d omega. Since the final form of the domain integral d1 is very much the same as that of the initial integral d0, it can be integrated by parts as before, and then we can come to the form of d1, that is d1 is equal to 1 by k integration del u2 asterisk w1 minus q2 asterisk b1 d del plus d2 where del square u2 asterisk is equal to u1 asterisk and q2 asterisk is equal to minus k del u2 asterisk by del n, and d2 is equal to integration omega u2 asterisk b2 d omega. So, so this procedure described earlier can be generalized in a natural way, introducing a sequence of higher order fundamental solutions defined by the recurrence formula. That what is the recurrence formula? That is del square u asterisk j plus 1 is equal to u j asterisk for j is equal to 0, 1, 2 etc., and q j asterisk is equal to minus k del u j asterisk del n. Okay. So, so and a sequence of functions b j and w j. So, b j plus 1 is equal to del square b j where j is equal to 0, 1, 2 and w j is equal to minus k del b j del n. So, the integral d0 can be transformed into the following series of boundary integrals only. So, then d0 is equal to summation of, because we have seen that it is d0, d1, d2. So, this is the recurring value, then we can express this domain integral that is the d0 in the form of a series expression, that is summation of j is equal to 0 to infinity 1 by k integration del u j plus 1 asterisk w j minus q j plus 1 asterisk b j into d del. So, it should be noted that this above equation is the exact form of the primary domain integral. Okay. So, this is a typical example of the formulation under boundary element method of the heat conduction equation. So, now we will move into the conservation equations that are necessary to be solved while we try to evaluate the temperature field, velocity field in case of melt pool generated during fusion welding. So, we have already discussed about the discretization techniques in the previous modules of this course. So, I am not repeating again. However, I will discuss about the conservation equations and their forms that is applicable to solve a typical fusion welding weld pool transport phenomena. So, so the mass conservation equation in case of in case of this when we are trying to solve the weld pool in case of TIG welding. So, you can see that so it is in the r theta z coordinate. So, where theta is not there. So, we are only focusing on 2D, that is r and z. Okay. So, radial and axial direction. So, it is a 2D formulation that is being discussed here. So, the mass conservation equation is of the following form, that is del del z rho u plus 1 by r del del r rho r rho v. So, here your u is the axial velocity and v is the radial velocity. Okay. So, the conservation of axial momentum can be written as del del t rho u plus del del z rho u square plus 1 by r del del r rho r u v. Okay. And so, we are talking about the axial momentum axial direction momentum equation, which is equal to minus del p del z plus 2 del del z mu effective del u del z plus 1 by r del del r r mu effective into del u del r plus del v del z plus j r b theta plus rho g b t minus t r. So, where j r is the radial current density ampere per meter square and then beta is the volume coefficient of thermal expansion, K inverse mu effective is the effective viscosity of a fluid in kg per meter second, rho the fluid density in kg per meter cube, and u and v I have already explained to you, and the z is the axial coordinate, that is axial distance. So, we have discussed about the momentum conservation equation in axial direction. Now, we are showing the momentum conservation equation in radial direction. So, the radial momentum can be expressed as del del t rho v. V is the radial velocity we have discussed in the previous slide, plus del del z rho v u plus 1 by r del del r rho r v square is equal to minus del p del r plus del del z mu effective del v del z plus del u del r plus 2 by r del del r mu effective into r into del v del r minus mu effective 2 v by r square minus j z b theta. So, like we have told that j r is the current density at the radial direction, similarly j z is the current density in the axial direction, whereas b theta is the azimuthal component of the magnetic field. T capital T so that is so and r is the radial coordinate, radial distance. So, the source terms in equation 2 that means the axial momentum equation, you can see that it consists of electromagnetic forces and Boschensky approximation. So, this is the source term due to electromagnetic forces in axial momentum, and this is the source term due to your thermal buoyancy. Okay. So, these are the two different source terms that is present in case of axial momentum equation, whereas in case of radial momentum equation you can see that there is only one source term, that is due to the electromagnetic forces alone. Okay. So, I mean so the conservation of thermal energy in terms of temperature I mean can be given by del del T rho Cpt plus del del T rho F, it should be FL, it should not be F1. Okay. Please correct. So, that is the liquid fraction into HF, that is the latent heat of fusion of the metal, plus del del Z rho U Cpt, where Cp is the specific heat at constant pressure and T is the temperature, and 1 by R del del R rho V Cp T. So, I mean so plus del del Z rho U Fl HF and then plus 1 by R del del R rho U, I mean rho R V Fl into HF is equal to I mean del del Z K effective del T del Z plus 1 by R del del R K effective del T del R plus 1 by sigma J R square plus J Z square. We have already discussed that J R and J Z are the current density in the radial direction and in the axial direction. So, the source terms in equation 4 are the Joule heating and the heat loss due to melting of the metal, melting that is happening at the weld zone. Okay. So, I mean like we have already discussed several times during welding. So, if I try to I mean show you a typical fusion welding of a butt joint. So, then this it looks like this. So, we are talking about this is the melt pool that evolves. So, although it is generally it is in 3D, but we are talking about the 2D formulation of the melt pool transport phenomena for you, for simplicity and for your ease of understanding. So, the continued here we have discussed about the conservation of the energy. Earlier we have discussed about the conservation of mass and conservation of momentum. So, these are the governing equations that are needed to be solved to understand and to investigate the transport phenomena that is present in case of I mean melt pool in case of fusion welding. And so, after these 3 governing equations, so then we will focus on the continuity of the current in terms of the electric potential, which can be expressed as del del Z sigma del phi del Z plus 1 by R del del R sigma R del phi del R. So, where phi is the electric potential, okay, in volt and so I mean and sigma is the electrical conductivity, that is I mean ohm I mean 1 I mean so it is can be I mean 1 by ohm meter. Okay. So, I mean so then to calculate the electromagnetic field and current densities, auxiliary equations based on Ampere's law and Ohm's law are needed. So, what are those auxiliary equations? That is B theta is equal to mu 0 by R integration 0 to R J Z, that is the I mean axial current density, epsilon d epsilon, where epsilon is a dummy function. Okay, and d epsilon is their I mean differential form, and capital J is equal to sigma I mean grad phi, and phi we have already discussed that is the electrical potential, and so sigma also that is the electrical conductivity. We have talked about the fraction of liquid, that is FL. So, please correct. So, all this will be FL. So, it is because of typo it is mentioned as F1. So, it should be FL, that is the liquid fraction. So, the fraction of liquid can be defined in this I mean model, in this I mean set of governing I mean conservation equations. So, FL is equal to 0 when T is less than equal to Ts. Ts is what? Here Ts is the solidus temperature. So, as we have discussed also during the I mean the casting solidification module. So, I mean that you already know, but if I try to draw a typical simple lens type phase diagram. So, then you can see that this is basically the top temperature is the TL liquidus temperature, and this one is the TS the solidus temperature, and then in between there is a mushy region. So, here the mushy, in the mushy region we are concerned about the liquid fraction, because now here here we are talking about the formation of the melt pool. So then I mean, so the FL is equal to 0 when the temperature is below or equal to Ts, and when the temperature rises then FL, so I mean liquid fraction generates. So then how to calculate the liquid fraction? Based on this expression, that TL is equal to T, that is the temperature of the solver or temperature of the I mean melt pool. So T minus Ts, T solidus, divided by TL minus Ts. That is the freezing range of that particular alloy or material that is under that is considered to develop the this melt pool transport phenomena. I mean investigate the melt pool transport phenomena. So here T must be greater than the solidus temperature and lesser than the liquidus temperature. So then only there will be a so liquid fraction will come in the form of fractions, and when the temperature reaches TL or it is beyond TL, then the liquid fraction FL becomes equal to 1. That means it is not anymore in the mushy region, and I mean complete melt pool formation has been done in the weld zone. Okay. So, for the turbulent model, because there is here this typical example is about the tungsten inert gas welding, the fusion welding in using tungsten inert gas welding. So, using non consumable electrode. So, there you can see the I mean the melt pool turbulence can very well generate. So, for the turbulent model, the standard 2 equation K epsilon model is employed. So, the conservation of turbulent kinetic energy can be expressed as del del T rho K plus del del Z rho U K plus 1 by R del del R rho R V K is equal to del del Z mu effective by sigma K del K del Z plus 1 by R del del R into R mu effective by sigma K del K del R plus G K minus rho E, where your G K is the generation of turbulent energy, kg per meter second cube, and epsilon is the rate of dissipation of turbulence energy, that is 1 by meter square second cube. Okay. So, I mean, so the rate of generation of turbulence energy is given by this expression, that is del del T rho epsilon plus del del Z rho U epsilon plus 1 by R del del R rho R V epsilon. We have already defined the epsilon as the rate of dissipation of the turbulence energy. Okay. So, so that so this is equal to del del Z mu effective into by sigma epsilon into del epsilon by del Z plus 1 by R del del R into R mu effective by sigma epsilon into del epsilon by del R plus C1 G K epsilon by K minus C2 I mean rho epsilon square by K. So, the generation of turbulence energy is given by G K is equal to 2 mu T del U by del R square plus U by R square plus del V Z del Z square plus half del V del R plus del U del Z whole square. So, the effective viscosity mu effective and the thermal conductivity K effective are calculated as the sum of their molecular and turbulent components. So, then mu effective is equal to mu plus mu T is the turbulent component of the viscosity, effective viscosity, K effective, that is the turbulent component of the thermal conductivity is K T. So, K plus K T, and small k only alone is the molecular component of the thermal conductivity, and then mu T is equal to rho C mu K square by epsilon, and Prandtl number PRT, that is the turbulent Prandtl number basically. So, then so is equal to Cp mu T by KT, that is the turbulent I mean thermal conductivity, which is equal to 0.9. So, the recommended values for the 5 empirical constants are C mu, I mean so that is what is I mean mentioned over here, that is C mu. C mu is equal to 0.09, and I mean so C1 C2 that we have shown over here earlier, that is somewhere around C1 is equal to 1.44, C2 is equal to 1.92, and sigma k is equal to 1, and I mean sigma epsilon is equal to 1.3, whereas C mu is equal to 0.09. So, these are the recommended values for the 5 empirical constants. Okay. So, these values are the recommended values. Okay. So, so moving ahead, so like we have discussed the energy equation in equation 4 here, yeah, where it is, yeah. So, this is the conservation of thermal energy. So, this, so here, so in this equation, so it describes the heat loss due to melting, and these terms are related to latent heat and vaporization of liquid fraction with time and position. So, it is derived from the enthalpy expression. So, what is the enthalpy expression? That is small h is equal to Cpt plus FL, again it should be FL HF. HF is the enthalpy of fusion. Okay. And then Mushi zone behavior. So, in the momentum equation, that is the axial and radial momentum that we have discussed in detail earlier. Yeah. So, this is the radial momentum and this is your axial momentum. Okay. So, I mean so in these two, I mean, so these are the equations. So, there is no extra term for flow in the Mushi zone, and viscosity in the Mushi zone depends on the volume fraction of solid particles. So, assumptions for viscosity variation. So, here the viscosity data for tin lead system is considered. So, as this assumption is used to simulate the flow in Mushi region, and sources of radial momentum. So, the shear stress applied by the flowing gas at the surface of the weld pool, and the Marangoni effect caused by the variation in surface tension with temperature. So, surface tension and temperature. So, surface tension changes with temperature gradients contributing to momentum variations. So, an equation for shear stress tau St can be expressed as is equal to minus mu, that is the viscosity, del V del Z is equal to del gamma del T into del T del R. Okay. So, I mean, where gamma is the surface tension. So, I mean, so these are typical the flow field that is calculated by finite volume discretization of the governing equation that I described till now. So, this is for different speeds. So, you can see that this zone 1 correspond to the region which is solid, and zone 2 which is the mushy region, and zone 3 which is completely liquid. So, at zone 3 the liquid fraction FL is equal to 1, and in zone 2 it varies between 0 to 1, and at zone 1 liquid fraction is equal to 0. Okay. So, I mean, so it is shown above for different melt velocities the how the melt pool evolves. Okay. And then so finally, we are coming to the last part of today's lecture, that is thermomechanical modeling. So, the residual stress simulation. So, importance of computational modeling. It is essential for understanding thermal and mechanical behavior in solidifying bodies, applicable to processes like additive manufacturing, welding and casting, where this residual stress generation is a very common phenomena, and thermomechanical modeling can be employed to estimate to predict the residual stress generated in these processes. So, the model assumptions, what are the model assumptions? So, the model to reduce computational complexity while calculating thermal and stress fields in the thermomechanical model, the following assumptions are generally made. So, what are the assumptions? Number 1 is strain due to solid state phase transformation was ignored compared to thermal and elastic strains, and creep strain was excluded from both thermal and mechanical simulations, and compositional changes during laser exposure were disregarded. So, this is a typical example shown for the additive manufacturing problem, and in the powder and liquid states of the material, stress strain and thermal expansion coefficients were assumed to be 0. The equation used to mimic actual process conditions and to match the experimental data is rho C del T is equal to delta K delta T plus Q. So, Q is the heat source strength, so that can be expressed by this expression, like that is Q r is equal to 2 P by pi r square and exponential minus 2 r square by r 0 square, wherein your small k is the thermal conductivity, capital T is the temperature, T small t time represents the interaction time between the laser heat source and the powder bed system, and as I told that Q is the strength of Gaussian volumetric heat source, which which is expressed by this equation over here, and which depends on the laser power, that is P is the laser power, and I mean R0 is the laser spot radius, and small r denotes the radial distance. Okay. So, the smaller is the radial distance, and your I mean capital P is the laser power, and your smaller is the laser spot radius. Okay. So, with this, so this is a typical example of how the I mean residual stress evolves at different build heights, where you can see that with the increasing build height, I mean the residual stress also increases, I mean from the base plate from where the build is getting developed. So, this is analogous to this increasing I mean residual stress evolution. So, with this we are done with this I mean module of welding transport phenomena and process modeling. So, we will meet in the next class with a new module. Till then, thank you.